So we have 104 of Leetcode, maximum depth of a binary tree. Before solving this question, let's look at the time constraints that we have. The number of node in the tree is from the range of 0 to 10 raised to the power 4. So the maximum node that we can have is 10 raised to the power 4. Now, before solving this question, let's compute the worst time complexity that we could have. So we will refer to time complexity table. Now in Leetcode C++, in 1 second, we can have 10 raised to the power 6 operations. So O of 10 raised to the power 6 will execute under a second. Now we have a maximum node of 10 raised to the power 4. So for O of n, O of 10 raised to the power 4 will actually execute under a second. Now for n log n, let's say n log n will be n log n is 10 raised to the power 4, log n will be 4. So 4 into 10 raised to the power 4 will also execute under a second because it is less than O of 10 raised to the power 6, right? And for n square, let's say, if you take n square, it will clearly not execute under a second because n square will be 10 raised to the power 8, and which is greater than O of 10 raised to the power 6. So it will exceed 1 second. So the worst time complexity that we could have is O of n log n, and n being 10 raised to the power 4 for the worst case, we can have 100 into n, right? We can have O of 100n and still not get a TLE. We are given the root of a binary tree and we need to figure out the depth of it. Now depth is simply you start from the root, account from it, and till you reach null, count the number of node that you face. From 3 till we reach null, we have 2 for the left subtree, and from 3 for the right subtree we have 3. So the maximum value is 3, so 3 will be our answer. Now we are going to discuss the recursive way to solve this problem. Now in recursion, I have told you before you don't have to actually think how internally recursion is working. All you have to follow is these 3 steps. Now before solving it using recursion, let us look at this question that we have. Now for root 1, the left subtree, the maximum depth that we have is 3. And for the right subtree, the maximum depth that we have is 1, 2, 3, 4, 5, right? So the answer will be 5, right? Now first step is assumption for the recursion. Now assume that we have a function where you pass the root of the subtree and returns you the answer. So let's say we have a function, you pass the root inside this function, root being 1, right? And it returns you 5 as the answer. Now what if you pass 2 as the root? What if I pass inside this function root left? So it will simply return me 2 as the answer because for the left subtree, the maximum depth that we have is 2, right? Now, what if I pass root right? If I pass the root right, that means I'm passing 3 inside this function. So first I pass 2 and I have a depth of 2. Then I pass 3. What will be the answer? It will account from 3, we'll get to null. So how many nodes that we have is 1, 2, 3, 4. So we have 4 as the answer. Now in these 2 statements, what we did was we went to the left subtree, calculate the depth, and then we went to the right subtree, calculate the depth. Then what we will do is we'll find the maximum of it. So maximum of left depth and maximum of right depth, which will be 4, right? 2 and between 2 and 4 we have 4. And but our initial problem was not to find the smaller subtrees. Our initial problem starts from the root, so we'll have to take account for the root. So we'll add 1 to the answer and this will be our answer. So what we do is to give you a perspective, we start from the root, we have a left subtree, let's say this is left subtree, and we have a right subtree. Now what we do is we break the problem into smaller steps, right? We had root. Instead of calculating the depth of root, what we do is we calculate the depth of left subtree and then we calculate the depth of right subtree, right? If the depth of left subtree, we store it in an integer variable, let's say left height, and for the right subtree we store it in an integer variable right height. And to compute the original question that we have, we'll compute the maximum of left height and right height and we'll add 1 to it. So this is simply breaking a bigger question into a smaller question, or step 2. right? What we'll do is, this is our, let's say this is our fx function where we are passing initially the root. Now we are breaking the problem into smaller steps. First we are going to the left subtree, so we'll calling root left, assuming ki it will return me the answer that is the depth of the left subtree. We'll store it in an integer variable int left, let me remove this, int left height. And what we do is then we call the right subtree root right. It will return me the depth of the right subtree and we'll store it in right height. So we'll write int right height. Now the original question was not to compute left and right subtree. Original question was to compute the depth of the root. So we'll have to take account of root. So we will do is we'll find the maximum of left height and right height and we'll add 1 to it, right? And this will be our solution, right? So we'll simply return it. So this is our code. Now the question is not complete, as in recursion you have to write the base condition. Now for the base condition, always refer to the constraint section. In constraint section we had the minimum number of node, that is 0, and the maximum 10 raised to the power 4. So third step is compute the smallest question and write it as a base case. So what could be the smallest question that you can have? You could be given root as null, right? Now what would be the depth of root as null? The depth will be 0. So this will be our base condition key. If the root is null, will simply return what? The depth of root, that is 0. And this is our complete recursive code. Now talking about the time complexity, time complexity will be O of n because we have to visit all the nodes at least once. And the space complexity will be O of n because we are using an auxiliary stack space.